fall time. When calculating the fall time, it is assumed that at 0 the input undergoes a step change to VDD, which turns Q1 on hard. The fall time is defined as the time it takes the output to decrease from 3.3 volts through a 70% change to 1.0 volts. During most of this time, the current through Q1 is much larger than the current through Q2, and thus Q2 will be ignored. This will make our estimate somewhat optimistic, but it helps to simplify the analysis. Initially Q1 is in the active region until VDG minus 1 less than minus VTN, or equivalently VDS minus 1 less than VEFF minus 1 is equals to VGS minus 1 minus VTN. This occurs when the output is discharged to 2.5 volts for VTN is equal to 0.8 volts. Next, Q1 enters the triode region during most of the fall time. This analytic derivation of the fall time is possible and has been given Hodges and Jackson 1988, but it is of little use during design. Possible and has been given but this is of little use during design. Instead, it is desired to find a formula for approximately equivalent resistor that would give a similar fall time. As mentioned, the current through Q1 is highly nonlinear as the output voltage changes from 3.3 to 1.0 volts. Figure shows a plot of this current as a function of the output voltage. If we could find a value for a resistor that gives approximately the same current as the actual transistor, the analysis would be greatly simplified. To find a resistor that is approximately equivalent to Q1, it is necessary to find an IV curve that is straight, passes through the origin, and results in the same fall time as obtained with Q1. One approximation that has been suggested previously is to use a resistor that is equal to the resistor of Q1 when VDS minus 1 is small, that is Q1 is hard in the triode region. Equation for this resistance denoted RTR is RTR equal to nu and C naught x W by L1 for 1 by nu and C naught x into W by L1 into VDD minus VTN. Here you can see the figure, the transient response of the inverter of figure for CL equal to 0.2 PF. Here you can see the figure, the current through Q1 as a function of the output voltage. However, as can easily be seen from figure, this approximation would result in a transistor that always has more current in the transition region, and Q1 has a better approximation is a resistor whose IV curve intersects the IV curve of Q1 at the edge of the triode region. This approximation is shown in figure as straight line labeled R equals. It can be seen that for the initial interval of the fault time, the current through R equivalent will be larger than that of Q1, and for the second part of the transition the current through R equivalent will be less than that through Q1. The voltage at the intersection point of IV curves of R equivalent and Q1 is VDD minus VT, and the current at the intersection point is the current of Q1 in the active region, that is ID minus 1 equal to nu n C naught x by 2 into W by L1 VDD minus VTN square. The value for R equal is the ratio for voltage of the current, that is R equivalent is equals to VDD minus VTN by nu n C naught x by 2 into W by L1 VDD minus VTN whole square is equal to 2 by nu n C naught x W by L1 VDD minus VTN. Thus, the approximately equivalent resistance to Q1 is twice R TR, the triode resistance of Q1. It turns out that equation results in transient times that are a little over 20% too low. Therefore, some designers modify equation to somewhat larger, according to R equivalent equal to 2.5 by nu n C naught x W by L1 VDD minus VTN. Others will simply use equation and add on 20% additional time after the estimate. Either approach is valid. Thank you.